All right, guys. So today we're going to go over a couple of different concepts. First, covering some important topics for exam PA, which we know one of which is identifying interaction terms. Are interaction terms even significant? So when we have in a linear regression model, we have interaction terms that represent the relationship between two different variables. So this could represent what is the joint effect of both of these variables. So not just what is the relationship of x2 on y, but what is the joint effect of x1 and x2 on y. And we're able to capture that by having this interaction term that measures the joint relationship between both x1 and x2 and y. And so that's why we have interaction terms in the first place. Sometimes our model is enhanced not just by the individual features, but by the joint interaction among the features. So that's why we have interaction terms. We can also check for the significance of the interaction terms by doing our typical statistical tests, testing if the coefficient value is equal to zero or if it's not equal to zero. If it's not equal to zero, that means it's significant and our model would benefit from including that in the model. If it is zero, then we fail to conclude that our model would significantly improve if we do include them in the model. So that's the purpose of interaction terms. When we think about model fitting, we know that there is overfitting and we know that there's underfitting. When we think of bias, bias is an underfitting condition. So underfitting means that we're not able to truly capture a lot of the details and nuances and the fluctuations in the data. So an example of this is if we have a certain data set that follows this quadratic, or even like you know parabola shaped trend, and we try to approximate this using this linear regression line, well then that's considered overfitting. We're trying to capture the high level trend, but it's not able to capture a lot of the systematic, a lot of the details, not able to capture the details of the data. And so that's underfitting. We're not able to capture a lot of the detail of our data. Overfitting is when we capture too much information, when our model is too trained, overly trained on the ins and outs of the data. It's too specific to the data. So, for example, if we have a model that's like this, and if we actually have this model, right? This is too tailored to the data. It is too specific to the data. When it's asked to generalize outside the data set, it may not create an accurate prediction because of how specific it is to the data set. So we want to have this balance of overfitting and underfitting, and that's why we have this entire concept of bias variance trade-off. We want to make sure that our models are not overfitting to the training data set. They have an appropriate level of model fit such that when they are asked to approximate and predict future values and other values that it has not seen before, then it can perform well on that. If we have models that are overfit to the training test or underfitting to the training environment, then they're not going to be able to generalize to new data points. So, for example, in the case of overfitting, it's our model is just not going to be able to generalize to other unseen data points. When it comes to underfitting, our model isn't is it's hard for the model to capture a lot of the nuances and systematic components of the data that it's missing out on. So it may predict just a simple linear increase where in fact it's actually a more nuanced relationship. So it's failing to capture that. One of the ways we can address underfitting and overfitting is through the hyperparameters in our models. So when we have random forest, we have ridge, lasso regression, we have different types of these models and different parameters that we can tune to address this entire concept of bias and variance and under and overfitting. Next, we have the entire idea of clustering. So we talked about bias variance trade-off, how this is an entire concept, and really any machine learning problem that you're trying to solve, you're going to try to create a model that captures their data set really well, but then also on unseen data points, it's able to accurately predict that as well. But that is referred to as supervised learning. That we have a label. We have a label that we're trying to predict. Now, when we refer to clustering, we don't have a fixed label. In fact, we have unlabeled data. We have data that it doesn't have a target variable. We're not trying to predict anything. We're not trying to classify anything. We're trying to learn from the data as is. We're trying to find, are there any patterns or trends or insights from the data that we can gather to create groups or categories where each group or each category is similar to one another. It has data points that are similar to one another, but the clusters themselves are distinct from one another. So this is what we call inter-cluster similarity and intra-cluster similarity. So inter means between and intra means within, right? Between the clusters, we want them to be different. We want their similarity to be as low as possible, right? So we want to minimize inter-cluster similarity. We want to minimize inter-cluster similarity, and we want to maximize intra-cluster similarity. We want to maximize how close together the points in each of the clusters are, but then minimize the distance between, but then minimize how similar the clusters themselves are from one another. So we want to have distinct clusters, but within those distinct clusters, we want to have closely grouped together data points. And so that's this entire idea of inter and intra cluster similarity. When we refer to model evaluation, when we're trying to evaluate our model, we want to evaluate it many different times. And so that's the entire portion of cross-validation comes in, is how can we take this data set that we have, how can we create different test sets, train our model a bunch of times, and how can we evaluate our model on different folds. So let's say we have 10 folds that we want to split our data set into. 9 of those folds will be used for training. Then the other fold will be used for testing. And we were able to do this 10 different times. We select 9, then we select another 9, and we leave the one fold for testing. In this way, we're training our model on different data points, and we're evaluating our model on different data points. So cross-validation is really able to get a better holistic view of how our model is performing rather than just having one training set and one testing set. We're able to get a multitude of those training and testing. We're able to see how our model is able to perform on those different folds. So it's a more holistic and a better approximation for our model performance. And so that's cross-validation. But this is just regular data. This is just the regular tabular data that that comes in data sets. What do we do when we refer to time series data? One of the things about time series data is we know that these values are dependent upon one another. The value at time 12 is probably going to be dependent upon the value at time 6. We have this dependent nature between values in our time series data. And one of the reasons that is the case is because we have seasonal trends, we have seasonality. We know that there's a dependency, especially in time series data. That's not the case in regular observations. In normal observations that we get, there's not a dependency between observations. Each observation is, for the most part, independent and they stand on their own. With time series data, it is sequential, it is seasonal, it has a trend, it is cyclic, it has patterns. Different points in time affect other points in time. And so there is this dependent structure within time series data that doesn't suit for regular cross-validation methodologies. And so that's why we can still use cross-validation, we just have to tweak it slightly to make it fit time series. So for cross-validation, we have these two different types of windows, we call it, that we can train our model on. We have our sliding window and we have an expanding window. A sliding window is only going to have a fixed number of observations that the model is going to train on. So if our length of the sliding window is n, at each iteration, at each cross-validation, we're only going to have n observation, and our window of training is going to shift by a certain amount, and we're only going to remain with the n observations. So for example, if we have n observations in one iteration, in the next iteration, we may shift our training to, let's say, include one additional observation, but then it's going to exclude the first observation. So we have this window where we are going to be shifting our training data set. On the other hand, we have expanding, where incrementally, upon each iteration, our training data set increases by one or whatever number that we want to set it to. And so that's what we refer to as expanding window. Our model is going to be trained on all of the historical data, whereas for sliding window, our model is going to be trained only on the most recent data. We're able to perform cross-validation on both because we're able to have a different training set for both. Both of these methods have their pros and cons. One of the disadvantages of this method is that because we're only using a portion of the training data, we're only using a portion of the training data, it may fail to capture a lot of the long-term trends. You may think, or you may think that, hey, we're still modeling, we still have a train and test. But one of the disadvantages of this is, let's say we have a time series data set, and up to this point is our training, and then onwards is our test that we're forecasting. But this is all still part of like the general training set, right? It's all part of the general training set. Training set. Now, this may have some long-term patterns that we fail to account for if we're only training on this portion right here. For example, this section may have some patterns that are associated with this section over here, right? Maybe this has a seasonal pattern. Maybe this is also associated with that seasonal pattern. So because we're not training on the entire data set, we're not able to capture those long-term trends. So that's one of the main disadvantages of sliding and expanding window and cross-validation in time series, is that we're not able to train on the entire data set, which leads to a less stable model over time. If we were able to train on the entire data set, then our model has seen both the short-term and long-term trends that could occur within the data, and then it's able to generalize to new unseen data points, and it's able to become more stable. It's able to be more stable over time, and so that's one of the improvements that we could have in cross validation and sliding and expanding window approaches. Next, when we refer to as so we talked about clustering a bit, and now we know that there's different clustering algorithms. There's k-means clustering, which is the standard form of clustering algorithm where you start off with a random initialization of centroids. You see which points are closest to the centroids. You assign that to a cluster. Then you recalculate the centroids. Then you assign the closest points to their respective uh, clusters that they're closest to, the centroids that they're closest to, recalculate the centroids, adjust the clusters accordingly, and then whenever you get to a point where two iterations consecutively have the same cluster assignments, then you've reached a point of convergence. K-means has converged, and you've terminated your algorithm. We also have hierarchical clustering, where this provides a more nested relationship of clustering. It describes how four clusters break down into three clusters, how those break down into two clusters. So we get these diagrams called dendrograms that describe the nested relationships between the clusters. So depending on your use case, you're going to cluster these different data sets differently. So that's why we have these two different clustering algorithms in the first place. When we think about our models, we talked about overfitting, underfitting. We also want to ensure that our models remain unbiased. And this is a core fundamental idea in really ethical machine learning. We want to make sure that our models are not just overfitting or not overfitting and not underfitting, but we want to also make sure that there is systematic biases that are not relevant to our model. Like they don't exist in our model. One of the ways that we can ensure that is through testing the model very rigorously, seeing different performance metrics, seeing if our model is biased to particular races, particular gender types. Is there certain demographics that our model is biased to? Having those in mind is going to allow us to create an unbiased and an ethical model. So those are some considerations we want to have when we're developing these models and when we're testing the models as well. So that's really what I wanted to cover. Again, so many different models that are also covered in exam PA. We have linear regression, we have logistic regression, we have all of the generalized linear models from Poisson regression to linear regression to logistic regression, and we have link functions, we have ways to interpret the odds ratio for logistic regression. We have so many of these generalized linear models when our data doesn't always follow a normal distribution, when uh, our data has certain trends that aren't normal or follow the assumptions of linear regression, then we resort to generalized linear models. And I have an entire video on generalized linear models that you can refer to. We also have neural networks. We also have KNN regression. Also have random forest regression, which are a collection of decision trees, and we're able to set many parameters on those number of decision trees, number of samples, min number of leaves to have number of trees, able to have a large variety of hyperparameters that we can tune, and this determines how much we overfit or underfit the data as well. And so we have these different models, we have these different clustering algorithms, all with the goal of understanding the data better, making accurate predictions, and ultimately gaining insight and telling some sort of trend within our data, some sort of creative element to our data. Is our data trying to explain something? Can we predict something that's going to be useful for us in the future? These are the models that help us with that. So that's all for this video. I'll see you in the next one.